Okay, let's go ahead and get started. So today what I wanted to do is finish our discussion of the quantization of a free quantum field theory. And in particular, I'll finish up by discussing causality in free quantum field theory and what are known as propagators or Green's functions in free quantum field theory, before moving on to begin our discussion of interacting quantum field theory, which is, of course, where things really get interesting. Okay. So let me just begin by reminding you of the upshot of what we discussed last class. So for a free quantum field theory, say of a single scalar field phi, yes? Oh yeah, sure, go ahead and turn on the light. I was wondering why it was sort of dark in here. That's probably why. I thought it was just me, I was tired or something like that. So for a free quantum field theory, say of a real scalar field phi that solves the Klein-Gordon equation, the way that we approach the theory quantum mechanically is we expand phi in terms of a basis of solutions to the wave equation. So the solutions to the wave equation are plane waves. And we expand phi in terms of the Fourier modes in this plane wave basis that we called AK and AK dagger, where here I'm using the shorthand where Kx is a shorthand for K mu x mu, where K mu is the energy momentum 4 vector, whose components are omega and k, and x mu is the usual 4 vector, whose components are t and x. And in a classical theory, phi is just a function, and AK and what I've called AK dagger here would just be the Fourier coefficients describing, say, some wave packet or some solution to the equations of motion. But upon quantization, phi is promoted to an operator, and AK and AK dagger are promoted to operators that act on the Hilbert space of this quantum theory. And we showed last time that the AKs and AK daggers obey the standard commutation relations of a set of harmonic oscillators. They, AK and AK dagger, commute if the indices k and k prime are not equal, and their commutator is equal to a delta function when the two indices become equal. What this means is that we should regard the system as an infinite set of decoupled harmonic oscillators, one for each momentum mode, and the states of the theory are the states in the Fock space, and they're just given by states of the form where you just have a bunch of these raising operators, AK1 dagger, say AKN dagger, acting on the vacuum state, which would describe some state with a bunch of particles of momentum K1 up to Kn. So that's it as far as free quantum field theory is concerned. The question that I want to end with, and a question that will naturally lead us to thinking about interacting quantum field theory, is the question of causality in free quantum field theory. So in particular, I ended last time by inviting you to think about what I referred to as the propagator, which is the quantum mechanical amplitude for a particle to move from a space-time point x, or from a space-time point y, to another space-time point x. Remember that phi is the observable that both creates and destroys particles. And so if you take phi of y and act on the vacuum state, that'll create a particle at point y. And if you take, and then you could project onto the corresponding ket with phi of x acting on the vacuum from the right, that would be a state where a particle has been produced at point x. And you could compute the overlap between those two states, and this would give you the amplitude for a particle to go from x to y, or I suppose it goes from y to x, because of the way that I've ordered these operators. And this is known as the propagator of the theory. And just about all of the class today will be spent in an exploration of these propagators and their properties. Are there any questions before I continue? So in a free quantum field theory, it's a reasonably straightforward exercise to go ahead and compute this propagator. So all I do is I plug in this formula. So did you all go home and tattoo this on your foreheads? I don't see this tattooed on many foreheads. Okay, you wouldn't really be able to see it if you tattooed it on your own forehead. That's why it's important to work together. Was there a question? No. Okay. Yes. Okay. So we can just go ahead and plug that boxed formula into this expression for the propagator. So we'll get two integrals. I'll call them integrals d3k and d3k prime, along with those normalization factors. And then you'll have the vacuum expectation value of what? Well, this linear combination of AK and AK dagger. Now remember, AK annihilates the vacuum when acting on it from the left, and AK dagger will annihilate the vacuum when acting on it from the right. So all you get is the expectation value in the vacuum of AK times AK dagger, because all the other combinations of AK and AK dagger would vanish, times this plane wave factor, so in e to the minus I kx plus I k prime y. Okay. And again, in order to keep the equation simple, I'm suppressing the mu indices that should be everywhere. So you should remember that these are 4 vectors and that I'm contracting indices of 4 vectors here. So what is this expectation value here? Well, if k is not equal to k prime, it's just equal to 0, because I can commute those operators through one another and use the fact that AK annihilates the vacuum. And if k is equal to k prime, then this gives you a delta function that you could use to do the k prime integral. So this gives you integral d3k over 2 omega k times e to the I k x minus y. So this is a completely explicit expression for the propagator of a free quantum field theory. And I'd like to just spend the next few minutes investigating its properties. Any questions before I continue?
Yes.
Yes.
So when you interpret that as the propagator...
Did I miss a minus sign? I missed a minus sign there. Okay, yes. Thank you. Yes, good.
But when you say that's the amplitude for a particle from y to x,
Yes.
is that because the first operator phi of y destroys the particle, and the next one...
Well, I mean, the way that I'm thinking about it is phi of y, so 0 is the state with no particles. Right. You act on it with phi of y, and that creates a particle at point y. And then you consider the overlap of that with the state phi of x acting on the vacuum. Okay. So in particular, I'm thinking of, say, phi of y acting on the vacuum as being the state with the particle at point y, phi of x acting on the vacuum as being the particle at position x. And then I'm considering the overlap between those two states. Okay, what do? So you take the the dual state to this, and what is that? That's 0 times phi of x, with no phi of x dagger, because phi of x is a Hermitian operator because the scalar field is real. Okay. So I'm taking the inner product between that ket and that bra. Okay. So that's the amplitude for a particle to be created at point y and travel to a point x. Is that clear, more or less? Any other questions? That's a sort of important point. We'll be returning to this. Okay. But yes, that's...
You said there's something wrong. You said there's a problem with this thing that would flip the cat, right? You said last time?
Yeah, and don't worry. That's what I'm going to be turning to in a minute. Yes. Okay. Okay, so what does this look like, at least qualitatively? So first, let's consider the case where x and y are time-like separated. So what this means is that x could be in either the future or the past of y. So for example, we could consider the case where y is just 0 and x, say, is t 0, 0, 0. So this is the amplitude for a particle that is created at the origin at time t equals 0 to travel, to arrive at some later time t in the future. Okay, so I'll take t to be bigger than 0. So let's just go ahead and compute that. So then d, so we can just perform this integral here. Well, we can just divide the d3k into spherical coordinates as an integral over the norm of k times some Jacobian factor k squared divided by the square root of k squared plus m squared. I'm going to leave out the factor of 2 because at the end of the day, I only want to calculate the qualitative behavior of this. And then you have an e to the minus I square root of k squared plus m squared. It's, of course, k vector squared. So that's what we call omega t. And then you could go ahead and just compute this integral. So in order to, I just want to understand its properties at late times. So to compute this integral, we can make a change of variables. So e, or what I called omega, is the square root of k squared plus m squared. So that means that e squared is k squared plus m squared. And so e times dE is k dk. So that means that this integration measure here, so that integration measure is k squared dk divided by e. We can then compare that to this formula. And what will that be? Well, you just need to multiply that formula by k over e, so that's k times dE. So this is dE times the square root of e squared minus m squared times e to the minus I et, integrated from m squared up to infinity. So that's just a simple change of variables in the integral. And what I'd like to try and do is understand how this behaves at late times. So at very late times, as t goes to infinity, this guy is going to oscillate very, very rapidly. So this integral will be dominated by its behavior where e is approaching where e squared is approaching m squared. So that means that this propagator will go like e to the minus I mt at late times. If you wanted to, you could go ahead and actually do this integral explicitly, and you would see this. There would be some factor of out front that depends on the mass. In fact, we can figure out what that is just by dimensional analysis, because this guy has dimensions of k squared. K has dimensions of mass, so it'll go like m squared. Actually, it's a little more. Okay. Yeah. So the important point, however, is that at late times, this propagator will fluctuate and is, in general, not going to be 0. Okay, let's consider now the more interesting case. So if x and y are space-like separated, so let's say, for example, that x is equal to 0, 0, 0, r, then we're computing the amplitude for a particle to be created at time t equals 0 at the origin, and then arrive at time t equals 0 some distance r away. Okay. So what is this? Well, this is integral d3k over the square root of 2 omega k times e to the I k dot x. No omega factor there because time t is equal to 0 for both x and y. So this is very similar to an integral that we did earlier in this class. Okay, we can go to polar coordinates and write this as the integral from 0 to infinity dk of k squared over the square root of k squared plus m squared. Again, I'll leave out that factor of 2 just to keep life simple. And then we have the theta and phi integrals when we do the d3k in polar coordinates. I'll use coordinates. So let's see, I've chosen x to just sit along the z-axis, and I'll use coordinates where theta is the angle off of the z-axis. So we do an integral from 0 to 2 pi of d theta times the measure factor sine theta, which I could also write as just an integral from -1 to 1 of d cosine theta. And then the integrand is e to the I k times r cosine theta. So we could just go ahead and do that integral. And it's 1 over IR times k times e to the ikr minus e to the minus ikr. Okay. And then instead of integrating this integrand here from 0 to infinity, yes, question. Is there a minus sign? Did I miss it?
K is the root of k squared plus m squared, or it's...
Oh, I'm sorry. Is there no, sorry. Is there no square root? Sorry, there's no square root there. Right, I just was stupid. Right, there's 2 factors of omega here. So there's no square root there. My apologies. Okay, good. Yeah, please go ahead and correct me if I make mistakes like that. Is there a sign mistake? I'm assuming there's a sign mistake. Okay. Anyway, it's not going to really matter. Okay, sorry about that. Did I make that typo anywhere else? No, I don't think I made it anywhere else. Okay, good. Okay, so let's transform that k integral, instead of thinking of it as an integral from 0 to infinity of the sum of 2 terms. I'll just note that those 2 terms are related by k going to minus k. So I can write this as an integral dk from minus infinity to infinity. So I guess I had a 1 over k here, so that gets rid of 1 factor of k. And then I'll pull out the IR out front. And then you have an e to the I kr. And I'd like to go ahead and do this integral by thinking about this as a contour integral in the complex k-plane. So in the complex k-plane, we're integrating a function that has a branch cut on the imaginary k-axis with a branch point at k equals to im, okay, coming from that square root here. Okay. And of course it has another branch point and a branch cut at k is equal to minus im. Okay. And aside from that, it's an analytic function in the complex k-plane. So I can perform this integral by deforming the contour of integration. So I start by integrating along this axis where k goes from 0 to infinity. And because r is positive, let's see, because r is positive, the integrand will vanish exponentially up here when k has positive imaginary part, so that this will be exponentially suppressed. So I can do the integral by deforming it into the upper half complex k plane, and the only thing that you get is, the only thing you have to worry about is the presence of this branch cut. And so you can perform this integral just by thinking about it as an integral along the branch cut. So I'll just introduce a variable z, which is equal to ik along the branch cut. Then this is the integral along the branch cut, say from m to infinity, of z e to the minus zr dz over the square root of m squared minus z squared. So if this contour manipulation and branch cuts and stuff like that is unfamiliar to you, I recommend that you brush up a little bit on your complex variables, because this is the sort of manipulation that's going to become very common. And the important point is that this is an integral of a positive definite quantity. And so in particular, this is not zero. So what this means is that even in our relativistic quantum field theory, just as in our non-relativistic case, there is still a non-zero amplitude for a particle to travel faster than the speed of light. Okay. So the question then is, why is it that quantum field theory makes sense as a theory that has causality? Okay. Because if things can travel faster than the speed of light, they can also go backwards in time. Is this argument clear, by the way? Everything I've said so far? Okay. The point is that although this amplitude that I've computed for you is positive, it does not actually have any observable consequences. So in particular, remember that in quantum mechanics, an observable is a, or maybe it's an, Hermitian operator. I never quite remember. And if two observables commute, then they can't possibly influence one another. Okay. So two observables that commute can't possibly influence one another. So that means that when I ask questions about causality, I really shouldn't be asking about the two-point function of the scalar field, this expectation value of phi x, phi y that I was talking about. Really, I should have asked the question of whether the commutator of phi of x, phi of y is non-vanishing when x and y are space-like separated. So for example, if phi of x is the operator that creates a particle here on Earth, phi of y is the operator that creates a particle in Alpha Centauri at exactly the same time in some reference frame, then if those two observables commute with one another, then the fact that an alien is creating a particle in Alpha Centauri can't possibly influence me creating a particle here on Earth. Okay? Even though the quantum mechanical amplitude, phi expectation value phi of x, phi of y, might be non-zero. two observables that commute with one another behave just like classical operators that are classical observables. And in particular, if you measure one of those observables, say by acting with phi on a state, then that can't influence the outcome of the other observable. Is that clear? So let's go ahead and compute this guy. So let's compute this commutator. So this is a calculation quite similar to the one that I presented to you earlier. So I'm not even going to take an expectation value in the vacuum state because, in fact, as you'll see, this commutator is not just an operator, but it's in fact just a number. That is to say, some number times the identity operator. So to see that, let's just compute this using the expansion of phi of x and phi of y in terms of their Fourier coefficients. So we have ak e to the minus I kx plus its Hermitian conjugate. And then we have its commutator with the same guy at k prime and position y. Now we can go ahead and use the harmonic oscillator algebra, and the only terms that will be non-zero are this term and this term. And their commutators will both just be a delta function that sets k equals to k prime. So we can write this as an integral d3k over the square root of 2 omega k times e to the minus ik x minus y from that first term, minus, because in the first case you had an ak dagger commutator, in the other case you have an ak dagger a commutator, which is minus of the first one, e to the ik x minus y. So if we compare that to what we wrote up here in our expression for the propagator, the propagator is the integral of e to the minus ik x of minus y. You see that this commutator is the difference between the propagator to go from x to y and the propagator to go from y back to x. And of course, I'm writing this propagator not as a function of x comma y, but as a function of x minus y, because due to translation invariance, you can always guarantee that the propagator will only depend on the distance, the separation between x and y, rather than on their individual positions. Okay, so indeed we see, as I claimed, that the commutator of phi of x and phi of y is just a number. It's not some operator. D is just some function. It's not some operator. And now we can use the fact that if x and y are space-like separated, then there is a Lorentz transformation that interchanges them, and in particular takes x minus y to y minus x. And so that this implies that d of x minus y is equal to d of y minus x for space-like separated points. So if it's not obvious that there's a Lorentz transformation that interchanges these 2 points, just think of the simple case that we had earlier where y was sitting at the origin and x was sitting at some distance r away, you could just imagine the rotation, say, about this axis here, that takes this point x over to this point here, and you see that you've taken r to minus r. Okay. So in this case, just by performing that rotation, you see that d of x minus y is equal to d of y minus x. Okay. So the commutator phi x, phi y vanishes for space-like separations. So this is an important point. In quantum field theory, the amplitude for a particle to travel across space-like separations and apparently violate causality is non-zero. But this effect is not measurable. There's no way that you could use this to send information, for example, across space-like separations, or to send information back in time, because the commutator is equal to 0, even though the propagator is non-zero. So that's the first important point that I wanted to make about this propagator. I next wanted to go ahead and consider some more interesting properties of this propagator that will be useful when we develop Feynman diagrams. But before I do so, let me just pause and see if there are any questions.
Just about the phi of x. So it is an observable?
Phi of x is an observable.
And what point is it correspond to?
Well, it's the observable that measures whether there's a particle at x. Well, not almost, yeah. It's the observable that creates a particle at x. That's a better way of saying it.
But I mean, so does it have some eigenfunctions such that?
Let's put it this way. If we were talking about electromagnetism, phi could be the electromagnetic potential. And that's an observable. Okay? You measure it. You get out your whatever those little things with the boxes and the squiggly signs on the front, and you measure the electric field somewhere. Okay? That's an observable. In the quantum mechanical interpretation, that's an observable that creates a particle. Okay, we call that a photon in the case of electromagnetism. But from a classical point of view, it's just literally the value of the electric potential, say, or the value of the electric field, depending on whether phi is, the potential or the field. I mean, it's an important point that the observable that is the value of the field is also the operator that creates or destroys a particle. Okay. That's the relationship between fields and particles. Yes, question. Has which property? Well, let's put it this way. Causality is, so for any local observable, if causality is preserved, if the theory is causal, the commutator at space-like separations has to vanish. But on the other hand, unless there's a really good reason, there's no particular reason for the actual two-point function, propagator as I wrote it down, to vanish. Okay. Let's say this a slightly different way. Okay. We're in a theory of quantum mechanics. So classically, it is impossible for a particle to travel faster than the speed of light. Okay. And why? That's because of the equations of motion of the particle are consistent with special relativity. Quantum mechanically, you know that particles travel on paths that don't solve the equations of motion. Okay. That's the point of the path integral approach of quantum mechanics. So that means that if it's the classical equations of motion that are telling particles they have to travel slower than the speed of light, in quantum mechanics, there's some sense in which you should expect that particles can travel faster than the speed of light, because they don't have to solve the equations of motion. In the path integral, you sum over all paths, including those that don't solve the equations of motion. Okay? And in particular, don't necessarily go slower than the speed of light. The question then is, how is that consistent with causality? And the answer is that it's the commutators that have to vanish, because those are the things that encode how one can actually use these quantum mechanical amplitudes to, for example, send signals or actual effect of measurable physics. Okay. Question?
So did we just get lucky, or could we have guessed with some very good a priori reason that the commutator here would vanish? Like just from seeing that the Lagrangian is would we be able to predict this?
Just because the Lagrangian is Lorentz invariant doesn't guarantee this property. For example, if m squared had the wrong, if m squared had the wrong sign, that would describe things that classically go faster than the speed of light. They can never go slower than the speed of light, but they can go faster than the speed of light. So it's not simply the Lorentz invariance of the action. I mean, I think there are many other ways of understanding why this thing has to vanish, okay, which maybe we'll encounter. But the short answer is that no. I mean, at this point, you could think of it as us just getting lucky. If we didn't, then we would really be in trouble. We'd have to come up with some other theory of multi-particle physics. Question?
Is it okay to think about the commutator function as
Yeah. Yeah, that's a pretty good definition of causality in quantum mechanics. Or in quantum field theory. Okay. Any other questions? Okay, we're getting into good stuff now. Okay. For time-like separation, this commutator does not vanish. So let's go ahead and study its properties in a bit more detail. So for time-like separations, let's go ahead and compute this commutator. So I guess I already wrote this expression down for you up here. So let's just go ahead and rewrite that expression. So at time-like separations, it is not the case that there is a Lorentz transformation that interchanges x and y. So there's no Lorentz transformation that takes t to minus t, even though there is a Lorentz transformation that takes r to minus r. The reason is that in special relativity, points in space-time are time-ordered. There's a definite sense in which certain events happen in the past or the future of other events. But there's no definite sense in which events happen to the left or to the right of other events. Okay? So that's another way of understanding why it is that this thing does not vanish at time-like separation. And just to remind you, sorry, no square root there, as we discovered, the expression was something like the integral d3k with that nice normalization factor of e to the minus ik x minus y minus e to the plus ik x minus y. And these two terms essentially came from the fact that you can think of, so this is a number, so of course we could always imagine taking its quantum expectation value in the vacuum state and getting the same answer back. And if you do, then you can think of this first term here as just the expectation value phi of x, phi of y, right? Because the integral d3k over 2 omega k times e to the I k x minus y is precisely what we calculated for this vacuum expectation value of phi of x, phi of y. And then we just subtract off the vacuum expectation value of phi of y, phi of x. So let's go ahead and compute this. And let's just consider the case where x0 is greater than y0. So x is in the future of y. So when x is in the future of y, you can go ahead and compute this. And what I'd like to do is I'd like to rewrite this expression for the commutator in a way which is a bit more manifestly Lorentz invariant. So I've written it here as an integral d3k over all of the spatial momenta, but I don't have an integral over k0 or omega. So what I'd like to do is note something very tricky, okay, which is that I can actually write this as an integral over the 4-vector momentum, k mu, provided I interpret the integral dk0 as a contour integral, and my integrand is k squared minus m squared times that familiar phase factor. Okay. So at first sight, it might not be apparent that this expression is equal to this expression. So let's go ahead and unpack that statement for a minute. Okay. So let's investigate this integrand here. Okay. So that integrand is some analytic function of k0, which has 2 poles. Okay. So that denominator here, let's write it out a little bit more explicitly. What is it? It's k0 squared minus k vector squared plus m squared. Or I could write that as k0 minus omega k times k0 plus omega k. So what we have here is an integrand which in the complex k0 plane has 2 poles, one at k0 equals to minus omega k, and the other at k0 equals to plus omega k. And remember the basic rule of contour integration, which is that when you integrate an analytic function around some contour, then you get 2 pi I times the sum of the residues at all of the poles of that integrand. So let's write this as the sum over all of the residues, let's call them z star, of the residues of f at these poles. So if that's not familiar to you, then again, go brush up on your complex analysis. Is this familiar to most of you, hopefully? Okay, good. And so what are the residues of this function at these 2 poles? Well, the integrand here goes like 1 over k0 minus omega k, and the residue is the thing that's left. So, for example, at this point where k0 is equal to omega k, then the residue is, so you get rid of this factor here of k0 minus omega k, and the residue is everything that's left over. So you get this, you get 2 omega k times e to the I kx minus y, evaluated at k0 equals to omega k. What is it? That's precisely this thing. Okay. And similarly, the contribution from this guy, this pole, is precisely this guy here. So, when we perform this contour integral, what we need to do is we need to make sure that we pick up the contributions to the from these 2 poles when we use this contour integration formula. Now, the final thing that we need to use is the fact that because x0 is greater than y0, we can close the contour in the lower half of the k0 plane. In particular, the contour, so here, let me just go ahead and erase that. The integral of that integrand down here is just equal to 0. And so, if we perform this k integral along the real k axis, provided we make sure that this contour goes just above the real axis, so that the two poles that we're talking here are inside this contour of integration where we close the contour in the lower half k0 plane, then we can express this commutator as this integral d4k. Okay. So just to reiterate, what we see is that if x happens after y, then the expectation value of this commutator is given by an integral d4k over 2 pi I times 1 over k squared minus m squared e to the minus ik x minus y, where when we write this integral, we need to be careful to choose the contour prescription. So when we write this integral, we remember we have the prescription that we include both poles in the complex k0 plane. Okay. So we choose the contour that goes above both of these poles. I'm sure there is. Where's my minus sign mistake?
You have to take a right-handed contour, I think, but you're taking a left-handed.
I have to take a right-handed contour. I'm trying to integrate this way. Okay. You're saying there's a minus sign out front? That's certainly possible.
Because then you can bring the I on top.
That's certainly possible. It's certainly possible that I've made a minus sign mistake. Yeah. That sounds
It's not like huge.
That sounds plausible. It sounds plausible that I've made a minus sign mistake by choosing the wrong orientation of the contour. Yeah, I think you're right. Good, thank you. Yeah. Okay. So let's investigate this quantity. So let me just define the following quantity. It's going to be this integral d4k, maybe up to that minus sign, and I define the integral by the prescription that when I do the integration in the complex k0 plane, I include both of the poles inside the contour. Or that is to say, I choose the k0 contour to be just above the real k0 axis. Okay, so if x0 is bigger than y0, then that's precisely the quantity that we computed above. Okay. It's the expectation value of this commutator. If x0 is less than y0, then we can perform this contour integral again, but we would close the contour in the upper half plane rather than in the lower half plane. And so that means we would just get 0 because we wouldn't get any of these poles. Okay. So what does that mean? It means that this slightly different version of the propagator is equal to a theta function of x0 minus y0 times the commutator of phi of x, phi of y. Okay. So in particular, if you want to calculate the commutator of phi of x, phi of y, only when x0 is in the future of, when x is in the future of y, then you compute it by performing this integral of k squared minus m squared, Fourier transformed, with this particular contour prescription that the k0 contour is just above the real axis. Okay. So in fact, this is an incredibly physical and incredibly important quantity. It's referred to as a Green's function, and in particular, it's known as the retarded Green's function. So in particular, this is precisely the quantum mechanical amplitude that describes the response of the field if you insert a source at some time in the past, x0, or at y0, and then you look at the result at some future time, x0. And it's a Green's function because it's a solution of the Klein-Gordon equation. So let's check that. So let's ask what happens when you act with the Klein-Gordon operator on this retarded propagator, this retarded Green's function. So here, d, of course, depends on both x and y. This is the covariant derivative d by d x mu, d by d x nu, g mu nu. Okay. I've written a little x subscript here to remind us that it acts only on x instead of on y. And if you want to go ahead and compute it, well, that's easy. You just plug into this equation. You get an integral d4k over 2 pi I. When you act with the x derivative, you bring down a factor of k. And so we get k squared. Well, you get a minus k squared because of that factor of I when you act with two derivatives with respect to x. Then you get plus m squared. So that comes from the d by dx squared plus m squared. Then you have this denominator times e to the I k x minus y. The numerator and denominator cancel, and you're left with an integral d4x of e to the I k x minus y, which is just the delta function, the four-dimensional delta function, that sets x equals to y. And you end up with a factor of I out front. It's an I, not a minus I, because there was a minus sign coming from the numerator over the denominator. So, hopefully, have you guys seen Green's functions before? So, a Green's function is the basic tool that you use to solve any linear differential equation, especially a wave equation. It's the solution to the wave equation that depends on two variables, x and y, that has the property that when you act on it with a wave operator, you get a delta function. So, for example, if you wanted to write down a more general solution to the wave equation with some sources on the right-hand side, you would use this retarded Green's function as a kernel that you would integrate your sources against. Have you guys seen that? So for example, this is typically what you do when you calculate solutions of Laplace's equation, for example, or the D'Alembertian in the presence of electromagnetic sources. And so we see that this two-point function we're computing is nothing more and nothing less than the usual Green's function that you would use when you would try and write down the solutions of wave equations with sources. You can immediately see now why these propagators are going to be useful once we start considering interacting theories. Because in the free theory, we had a wave equation where d squared plus m squared of phi is equal to 0. In an interacting theory, d squared plus m squared of phi is going to be something that's not 0. You're going to have some source there, and you're going to need this propagator to understand how phi responds to the presence of that source. So this d sub r, the retarded Green's function, is a Green's function. And it's called the retarded Green's function because it's the one that has a theta function of x minus y out front. But in fact, when I went through this argument that showed that d was a Green's function, I didn't use that contour prescription anywhere. Okay. So in fact, any choice of contour in the K0 plane will give a Green's function. The choice of contour that we used in the definition of this retarded Green's function was one that doesn't treat past and future democratically. Okay. It's the one that vanished when x0 was less than y0. So in our future studies of quantum field theory, we'll actually find much more useful a slightly different choice of contour. So the most useful propagator is known as the Feynman propagator. And that's defined by the contour prescription, where when we perform the integral, here, let me scroll down a little bit. When we perform the integral in the complex K0 plane, we have these two poles at minus omega k and plus omega k, and we'll choose our contour to go below the first one and above the second one. So this Feynman propagator is again just the integral d4k. So traditionally there's a factor of I that's just inserted for future convenience of k squared minus m squared times e to the minus I k of x minus y, with the prescription that we use this contour of integration. Okay. And in fact, there's a very simple way of encapsulating the statement that we use the contour of integration that goes below the first pole and above the second pole. That's just to add a small imaginary part to this denominator here. Okay. So you imagine that epsilon is an infinitesimally small number, which will be taken to 0 at the end of the calculation. And all this epsilon does is it slightly rotates the contour. Okay. So it rotates the contour to put, it rotates the contour, basically. It takes a straight contour like that, and it turns it into one that's rotated up slightly, so that you go below that first pole and above that second pole. Okay. So that's the definition of the Feynman propagator. What is its physical interpretation? Okay. So first, let's imagine calculating this when x0 is, say, bigger than y0. When x0 is bigger than y0, you perform the contour by completing it in the lower half of the x0 plane, because that's where the integrand vanishes. And in that case, you only pick up one of the poles, and you don't pick up the other pole. Okay. Now, remember that one of these poles gave the expectation value of phi x, phi y, and the other gave the expectation value of phi y, phi x. So that means that when x0 is bigger than y0, you get the expectation value of phi x, phi y. And likewise, if y0 is bigger than x0, then you complete the contour in the upper half of the complex K0 plane. You pick up this pole here instead of the other one. And so you get a second term that's theta of y0 minus x0 times the expectation value of phi of y, phi of x. Okay. So what's going on with all of these thetas here? So what's going on is that all we're doing is we're calculating the 2-point function of phi of x and phi of y, And we're putting in here by hand the instruction that whichever operator happens later goes on the left. Okay? So we sometimes use a shorthand. We call this a time ordering of operators. Okay. So this symbol T is just the instruction that everywhere you have a T in front of a bunch of operators, what you're supposed to do is order the operators such that the earliest operator is farthest to the right and the latest operator is farthest to the right, to the left. Okay. So earlier operators are on the right. So next class, when we start developing the rules for the computation of scattering amplitudes in quantum field theory, we'll see that it's these time-ordered expectation values that enter. Are there any questions on this? So far this is just a definition. Okay. So let me just introduce one more definition. So far we've just been working with these propagators in position space. But you can see that they all will take a form that's going to be very simple in momentum space because they all have those integrals e to the I kx appearing. So we will often like to work in momentum space. So we will define, for example, the Feynman propagator with form momentum k to be the integral d4k of the Feynman propagator in position space. And then you can see from this equation up here that that's just I over k squared minus m squared, with this little factor of I epsilon to remind us which contour to take if we do a k0 integral in the complex k0 plane. Yes, question? Oh, I'm sorry. Yeah, what am I writing down? I'm writing down nonsense. Integral d4x e to the I k x minus y. Okay, sorry. I was a little too fast there. K squared minus m squared plus I epsilon. Thank you. Good. Okay. So there's 2 points that I want to make about this expression before we conclude our discussion of free field theory. So the first is that this propagator has a pole when k squared is equal to m squared. And remember, k squared is equal to m squared is just the classical equation of motion for a plane wave. That's just the statement that the plane wave e to the I kx solves the classical equations of motion. And so we sometimes say that k squared equals m squared is the statement that the momentum is on shell. So what we imagine is that we have, in k space, we have some shell where k squared is equal to m squared. So it's a little hard to draw. It'll look like this. Be some sort of surface in k space that looks like this. And whenever the form momentum lies on that surface, the plane wave will solve the classical equations of motion. And so we say that's on shell. And when we're considering interacting quantum field theory, the slogan that we'll need to keep in mind is that poles in Green function correspond to particles. So the relationship between the existence of this particle state with mass m, and a pole in the Green's function is something that's going to generalize, and a lesson that will hold true in interacting sort of more interesting quantum field theories. And the second statement to make is that the K integrals that we're doing here involve values of K which are off shell, i.e. where K squared is not equal to M squared. Okay. This is just restating what we stated earlier, which is that when you're thinking about a theory of quantum mechanics, you include contributions coming from paths where the particles don't solve the equations of motion. Okay. And in this case, working in Fourier space, this means that K squared is not equal to M squared. Okay. So this is everything I wanted to say about free field theory. What I'd like to do now is at least begin to introduce some features of interacting quantum field theory. But before I do so, let me see if there are any questions. No questions? Okay. So we've basically bludgeoned to death the subject of free field theory. There's really not much more that we could say about it. Okay. Interacting quantum field theory is, however, a much more complicated subject. And the basic problem of an interacting theory, that is to say, a theory where the Lagrangian is no longer just quadratic in the phi's, but might have phi cubed, phi fourth, or higher order terms describing interactions between these particles, is that we can no longer simply expand phi in terms of this basis of raising and lowering operators, and expect these operators AK and AK dagger to satisfy the usual algebra of the creation and annihilation operators of the simple harmonic oscillator. And so in particular, the Hilbert space of an interacting field theory is not just the simple Fock space that we described earlier. It is not just an infinite number of non-interacting simple harmonic oscillators. Okay. So multi-particle states cannot be described simply, for example, as AK dagger prime acting on the vacuum state. Okay. So before we begin discussing how we'll do computations in these interacting quantum field theories, we first need to talk a little bit about what the Hilbert space is and what space of states we're going to be studying when we study interacting quantum field theory. So the question is, what in general will the Hilbert space look like? So first of all, there should be a vacuum state, a state with no particles that we'll continue to call 0. Okay. Although in some textbooks, the vacuum of an interacting field theory is distinguished from the vacuum of a non-interacting field theory. Sometimes people call it omega. So for example, I believe that's what Peskin and Schroeder does. To keep life simple, we'll just use the same symbol that we've been using in non-interacting field theory. And we still want one particle states, so we should still have one particle states states describing a single particle that will be labeled by some momentum with an energy that's given by the square root of k squared plus m squared for some value of m. The reason being that the expression omega squared is k squared plus m squared is really just special relativity. There's no assumption about what sort of interactions you might or might not have in the field theory. That's just the relationship between energy and momentum in special relativity. And we now expect that there will be multi-particle states. And what I would like to do is label those multi-particle states by a total momentum, k, along with some other quantities, some other parameters, that I'll call lambda. So, for example, if you have a two-particle state, then you would think of k as the total momentum and lambda being the relative momentum, the difference in the momentum between those two particles. Okay. So, for example, relative momentum. But there could be other parameters, so lambda will really denote some collective set of parameters that could be either continuous or discrete. Okay. And these states will have an energy again determined by special relativity. That should be the square root of k squared plus m squared for some value of m that depends on lambda. Okay. And the point is that because the label lambda is continuous, it includes, for example, relative momentum, which is a continuous variable, these multi-particle states should exist for a continuous range of values of that parameter m lambda squared. And in particular, they should exist for all m lambda squared, which are greater than or equal to 4 times m squared. So m is the mass of a single particle state. If you have two particles, they'll have mass 2m, and so the square of that mass would be 4m squared. Okay. So whenever you have two particles you would have no relative momentum, you would expect their mass squared to be just 4m squared. But if you give them some relative momentum, that would increase the effective mass. So if you want a picture, then you could draw a picture in momentum space. The allowed states you could draw, say, in the P0 plane. So here, let's take the horizontal axis just to be Px, for example. Yes, question?
If they have some sort of binding
Yes.
energy,
I'll come back to that. Okay. So yes. So for right now, let me just assume that there's no binding energy. When I come back to that, either maybe or not by the end of this class, but sometime next class, we'll discuss what happens in cases where there is binding energy. Okay. In particular, we know that they should exist in a continuum when there's no binding energy in the case here. There will also be special cases where there could be binding energy. Good. Good question, yes. So let me just draw these states, sketch them in the P0, Px plane, for example. So the one particle states will live here. Okay, that's the hyperboloid where p0 squared is p squared plus square root of p squared plus m squared. They'll live along that line. And then there's a second line where p0 is equal to p squared plus 4m squared. And there'll be a continuum of states that will fill out the region everywhere above that line. Okay. And then there may even be other bound states, for example, that would give you other lines in this px plane. And the assumption that we want to make is that these states should form a complete basis of states. So that, for example, the identity operator should be equal to the projection operator onto the vacuum plus the projection operator onto single particle states plus the sum of all possible projection operators onto multi-particle states labeled by both these extra parameters lambda as well as the total momentum k. Okay. So the first question that we want to ask then is, how do these states contribute to observables? So let's just consider the simplest sorts of observables, namely those we were considering earlier, the propagators phi of x, phi of y. So let's just very briefly consider what would happen in a more general interacting theory where we have all of these more complicated states and how they would influence this two-point function, or this propagator phi x, phi of y. So what I'd like to do is just take this identity operator and insert it right between phi of x and phi of y. So we can just go ahead and write that out. You know, quantum mechanics is an exercise in writing one in very complicated ways. So the first term is just the product now of these expectation values of phi of x times the expectation value of phi of y. The second term is a similar expression where the intermediate states are now one particle states. And then finally, there will be some complicated contribution coming from all of the multi-particle states. Okay. Okay. So let's start. Yes, question. Okay. So let's just consider the case where we have a free theory. So consider the two particle states. So the two particle states were labeled in the free theory by two momenta, k1 and k2. Okay. In an interacting theory, I no longer know exactly how I should be labeling these states. Okay. I know that they should carry a total momentum, which in the free case was k1 plus k2. But I also know that they could in principle be described by other parameters as well. For example, in the free case, the state k1 and k2 is described by its total momentum k1 plus k2 and the relative momentum k1 minus k2. I could label two particles, instead of labeling two particle states by the momenta of the two particles k1 and k2, I should feel free to label them by their total momenta k1 plus k2 and their relative momentum k1 minus k2. So in this case, for the two particle states, lambda is just the continuous parameter k1 minus k2. And when I write a symbol like the sum over lambda, I really mean an integral over all of those continuous parameters, as well as a sum over whatever discrete parameters might appear. I'm trying to write down the most general thing I can, making as few assumptions as possible. For three particle states, there would be two relative momenta, and so on and so forth. Okay. There could be many species of particles. There could be many complicated ways that they bind together. So I don't really want to make any assumptions about lambda at this point. Instead, what we're going to do is write down a general formalism to think about this, and then we'll start considering specific theories, and then we'll go ahead and start computing these things. Other questions? Okay. So I see that I'm out of time. I didn't quite get a chance to do everything I wanted to, but rather than trying to cram it all into the last few minutes, maybe what I'll do is I'll just stop here unless there are any questions, and we'll pick this up on Tuesday. Okay, and there is a new problem set to pick up, so don't forget that on your way out. Okay, thank you.